answer. All right, thank you. Or else I will forget. Okay, so okay, so types of matrices, yeah. All right, what is the first one in the notes? Zero matrix. And zero matrix is O. It's not a zero, yeah? It's a big capital O. And with the entry 0. Make sure you differentiate your letter O and your number 0. Okay, so this is called a zero matrix. And we have in general M by N matrix, right? We can also have N by N matrix, a square. So if you have M by N matrix, you write like this. If you have N by N matrix, sometimes you write that, sometimes you just put this, okay? So zero matrix is not necessarily square, okay? Not necessarily square, it can be M by N. And if you want to have a square matrix, it's not an oxygen, but it's a 2 by 2 zero matrix. Okay. The next one is a square matrix. Square matrix. Yeah, square matrix. So this is just the row equal to the column. Okay. Next, I mentioned about the identity matrix. Okay, this is not just like school. You just write out the entry. You have to know the definition in general because you have to be able to prove in general if given some properties of matrices. Yeah, that's why I write in terms of this. The next one is square matrix. So M is N, right? So you have this matrix. The third one is the identity matrix. I, okay, I, and it has to be square. So we put IN. And suppose this is AIJ. Okay, sometimes I use like this. Sometimes I use this. But they are similar. Okay, don't ask me why. Kadang angin dia angin parenthesis, kadang angin dia angin bracket. So let me stick with this. But you know the identity matrix is square, and then you remember that the diagonal entries are all 1, the rest are all 0. Okay, so this is how you write. The inside is equal to 1 when I is J. Remember A11, A22, A33, that is the diagonal. And if I is not J, it's equal to 0. So if you are given this kind of situation, you have to know what it means. You cannot just get used to writing up the identity like this. Right? This is in general. In general, yeah? Or N by N. It's a square with the diagonals equal to 1 and the rest is 0. Okay, my next question is, what do you call this? Tak payah panggil nama lah, you just type, or if you don't know, you can tell me you don't know. What do you call this? and so on. Itu macam buat ayat. Apa tu? Ada siapa-siapa yang tahu tak? Dot, dot. Ish, memanglah, tu cara baca. The name. Tak tahu? Tak tahu? Jadi macam komedi. Saya pun tak tahu. Saya tahu. You know? This is the name. Tahu tak? Tak tahu kan? Hari ni saya belajar satu term. Cuba Google. Ellipsis. Hush, jawapan macam-macam. Sebenarnya setengah orang memang panggil dot, dot, dot. Nampak tak? Nampak? Ellipsis. Informally, dot, dot, dot. Without altering the original meaning. You think suka-suka hati nak dot, 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 it has to be 3 dots. If it's 2 dots or 4 dots, it's not dot, dot, dot. It's not an ellipsis. So it has a meaning. Yeah? And dot, dot, dot at the end means and so on, never ending. If dot, dot, dot in the middle means it has a certain pattern. Right? You know math is about pattern, right? So hari ni dah belajar satu term baru. You ask your senior, math senior. Kalau kenal. Tahu tak apa simbol ni? Kalau tak tahu tak boleh dapat degree math. Belagaklah sikit. Hana tahu kan Hana? Hana, ada tak Hana?
Tahu lah.
Sebab saya dah cakap dalam kelas. Kan? Alright, okay. Next one is okay, transpose, yeah? I mentioned on Sunday. Transpose, you have learned this before, right? Transpose of a matrix. Soalan. How the digits will be for ellipsis? Tak faham soalan lah saya. Kausalia? Apa soalan dia? Digit apa? Mana orang yang bertanya ni? Mana? Angkat tangan. Angkat tangan. Kalau angkat tangan, kita akan pergi ke first person in the screen. So I can see. Otherwise, you're probably in the third page. Yeah, Kausalia? What's your question about the digit? Boleh on the mic, unmute.
Hello, doctor.
Yeah.
So for the ellipsis, right? If we didn't write that how the digits will be.
This ellipsis just means that you cannot write in full. You will write like this, right? 1, 2, 3, dot, 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 maybe until 10. Okay? So in this case, the dot, 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 you know it's 4, 5, 6, 7, 8, 9. Because that is how the pattern, right? Or you put this, dot, dot, dot. How can you write? You know already, the one before this maybe 998. So it's just dot, dot, dot means the missing pattern, the missing elements in between. If you go
Then
just 1, 2, 3, that's it at the end. So this is the name of the symbol, is dot, dot, dot.
Okay, then for the identity matrix, how the pattern will be, doctor?
Just now, the one that I erased, because it's all 1, 1, but it's n by n, right? You cannot write n times you don't know, so you put dot, 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 1. And then there's a 0, 0, 0, dot, 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 0. Meaning 0. 0, dot, 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 0. 0, dot, 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 1. Or you can put 0 here. 3, yeah? So sometimes people just write 1, 1, dot, 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 1, big 0 here. Yeah, that
Oh.
means the rest they are 0. And the identity is there.
Okay, doctor. Thank
So
you.
your question is actually for the identity matrix and not for
Yes, doctor.
all right. You can lower your hand. Nanti saya ingat ada soalan lagi. Okay, so transpose A is Aij, M by N. A transpose is Aji, N by N. As I said, you have to know how to read the symbolize or the symbol, not only that you write all in full, because sometimes you cannot write in full. Like M by N, how can you write in full M by N, right? So if I write in specific, so the transpose means row becomes column, column becomes row. So the first row becomes column, and the second row becomes the second column, or column becomes row. So this is how actually it is. Some of you mentioned probably think that it's the mirror image, but it's not true because it might not be square. Yeah, if it is a square, you might say that it's a mirror image. So the transpose is this, and then you say transpose like this, which is actually one first row becomes column, row becomes column, right? You think always that it's a mirror image, but this is only true for the square matrix. But in general, this means the row becomes column, the column becomes the row. So the 2 by 3 becomes 3 by 2. Right, you have learned this, right? Siapa yang tak on video sendirilah, siapa yang nampak dia. Okay, that's number 4. All right. The next one that you should know is, saya dah suruh baca semua kan? Properties of transpose, ya? Properties of transpose. If you transpose a matrix and then transpose again, then you will get that matrix back, right? Because you write as this, you write back, you will get A back. So double transpose, you get it back. If you add, then you transpose. This is the same as transpose first, then add. All right. The third one is different. When you multiply, then you transpose. This is B transpose first, so you read from the right, A transpose. So remember this property. So in general, I do this because if this is A1, A2, maybe you have A1, A2 until AN transpose. That's why there is a dot, dot, dot. Then you go from the right. So this is AN transpose. Before AN, because this is 1, 2, it has to be increasing by 1 or decreasing by 1. You have AN minus 1 T dot, 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 A2 T, A1 T. Okay, transpose, you had to do it from the right. Okay. Ini rule number berapa ni? Ni ada soalan okay. Okay, kata okay, tunggu sekejap, saya tunggu sekejap. Although this is actually in the notes that I put in the e-learning. Biasalah kita suka baca tulisan sendiri kan, nak juga tulis kan. But it's okay. But sometimes I cannot wait. That's why the very first time I started this notes is by writing everything on the board. And then the student need to copy and it will take so much time. So I started to write with hands and then type. Banyak masa ni. Okay. And then you will say, alah, photostat aja lah, lagi murah. That means you don't appreciate the hard work. Okay. The next one is number berapa? 5 eh? 5. Okay. Symmetric matrix. Okay. A matrix is symmetric. And this is for square matrix, yeah? Square matrix. A n by n. A transpose is A. Meaning, the first row has to be the same with the first column, right? The second row has to be same as the second column. So if you write A is Aij, then A transpose has to be equal to A. Okay, so rows and columns, they are similar. We can come up with any example. 67. Oh, you know, the number of participants. Oh, I can screenshot ni. Why? Because 67 is my lucky number. Because it's my birth year. Hahaha, tu mudanya saya. Okay. Alright. So, example. Wow, boleh gang. See, I'm as old as your mom, as young as your mom, right? Yusof, you anak keberapa?
Bongsu, madam.
Ah, okay. My youngest is about your age too.
Is it the one named Farhan?
Oh, ada skodeng ya?
No,
I mentioned I have Farhan, right?
uh,
I'm just kidding. I'm just kidding. No, that is my second one. The third one. Yeah. I have 3 boys. All right. The first one is actually doing his PhD in mathematics in UTM. We are almost finished. Okay. Dah, setiap orang saya kata tadi ada boleh dapat. Oh, terus hilang 66. Siapalah yang tak suka saya punya lucky number ni, dah keluar dah. Okay, I mentioned that everyone can come up with their own example, right? For symmetric matrix. Like if I put 1, 2, 3 here, I put 1, 2, 3 here, anything there, it doesn't matter, right? Because then if I put 1 or -1 here, I put -1 there. So 1, 2, 3, 1, 2, 3, 2, right? So actually, whatever you put at the diagonal, it doesn't matter, but whatever you put here must be the same here, right? So you put here, you put here, you put there, you put there. So this is actually the rule. Okay, ini semua dah belajar, tak heran lah kan? Alright, next one, maybe you have not heard about this matrix, is skew symmetric matrix. Skew symmetric matrix. Okay. Best tulis kat papan ni boleh padam-padam macam ni. Alright. Skew symmetric matrix. And for this matrix, it's also a square matrix. And a matrix is called skew symmetric if before that, I think the last class, whose photo that I took? Yusof, yang saya tanya soalan tu. Is it Amirul? Zakwan? Yang saya share dekat. Is it you? Are you here?
Yeah, Prof.
Okay. So you are the student of my student.
Student of my student.
In UITM, your lecturer was my student, right?
Yeah, Dr. Afika.
Okay. Dr. Afika is one of my, I have now already 34, about 39 PhD students graduated. So Dr. Afika is number 22. Hana? Hana nombor berapa? Dah kira belum? Dia bagi semangat untuk grad kan. Okay, anyhow. Okay, dah. Ada yang dah membacakan, ada yang PM tepi, dan ngeri lah nanti saya nak tanya soalan sampai mana ni hari ni. Dah baca sampai habis dah chapter 1 ni. So skew symmetric matrix is also a square matrix. Okay, a square matrix, and we have A transpose is negative A. It's a little bit different than before, right? Before is A transpose is A, but this one A transpose is negative A. So how do you think about getting one example out of this? So you think you have to think about what if you write in general? Yeah. Yusuf?
Yes, madam. I just wanted to clarify. This still goes under A n times n, right? Is it still
Yeah.
square?
Yeah, I mentioned in the beginning that A has to be a square matrix. Otherwise, you cannot find this.
Okay, thank you.
So what you will write is that if A is Aij, right? A transpose is Aji, right? Okay, and negative A, although we have not seen the operation, is actually just negative Aij, right? Every entry we multiply by negative. So to see that these two are equal, so you will write Aji is equal to negative Aij. Okay, so this is a matrix that we want to think about. What if I is J? If I is J, you will get I is J, yeah? I is J, I is negative I. Can you solve this? Two I is 0, so I is 0. Okay, when the case I is J, it has to be 0. Otherwise, you will not get that I is negative Ai. Impossible, right? If I is not J, then it has to be the negative of each other. Okay, so let's try this and come up with an example. So if you put A is probably 0, right? We have to have 0. And if this is 1, maybe this is negative 1. This is what it means by this condition. Okay, so if you want to check, you check using this. So you will write A transpose, you transpose, right? Right, this becomes this is A transpose, which is actually equal to negative A, right? Because it's negative. So for skew symmetric matrix, actually, the condition is that if I is J, we have to have 0. If I is not J, this has to be negative of each other. Okay. That is why I have the example that all example for skew symmetric, you will see the diagonals are 0. If the diagonal is not 0, you can try. Because you will take the symmetry is the same number, but how can a number be equal to the negative? If you put a 1 here, then you take the symmetry still 1, but how can 1 equal to negative 1, right? So that is why the diagonal have to be 0 and the opposite has to be negative of each other. Why do we have this symmetric and skew symmetric matrix? Because there is this theorem that says that every square matrix can be written as a sum of a symmetry matrix and a skew symmetry matrix. Okay, you Google and see why. Why do we want to write it as a sum of these two? There must be a reason. Okay. So it's a good thing to know because there's also an application out of this.
Professor.
Yeah.
So you clarified that if I equals to j, then aij should have to equal to 0. Only then it can be skew symmetrical, right?
To be skew symmetric, that is the condition. But doesn't mean that all matrices with all diagonals 0 is skew symmetric. It has to have the second part, right? The opposite has to be negative.
Negative. So there's no chance for something that where I does not equal to j will become skew symmetrical.
When I equals to j, this is talking about the diagonal. That is what it means by I equal j. Okay, for aij, when I equal j, that gives the diagonal 1, 1, 2, 2, and the rest. So this symbolizes the diagonal. When I is j, this is 0. This will give this condition for skew symmetric. So if I give you a matrix, you see any of the diagonals are not 0, automatically it's not.
Okay.
But you cannot say because the diagonal is not all 0. Why? You have to write A transpose is not negative A, because that is actually how you should write it, skew or not skew symmetric. Okay. All right. Okay. So this theorem says any square matrix can be written as a sum of a symmetric and skew symmetric matrix. A is S plus P. So S is for the symmetric, P is for the skew symmetric. Why P? Symmetric is S. You know why P? Because this comes from the Malay. Not long time ago when we learned in Malay. Skew symmetric in Malay is symmetry pencong. That's why it's a P. Kertas conteng. Actually, if I put skew symmetric SS would be confusing a little bit, right? S plus SS, just short sendiri pula kan? And there is a formula. This is the formula. Yeah, this is the formula. You give me any square matrix, I can give you that it is a sum of S and P, and this is the formula of S and P. As an example, yeah, Yusuf, you like to talk, right? Give me a square matrix, 2 by 2.
Let's go with 4, 7, 7, 4.
4, 7,
7, 4.
doesn't have to be symmetric.
Oh, doesn't has to be. Okay, then 1, 2.
1, 2. Okay, we want to write this as the sum of a symmetric and a skew symmetric. Okay, cuba jaya. First, cuba jaya. Why I know I can cuba jaya? Because I know that the skew symmetric has to be 0, 0, right? Right? So if this is 0, 0, this has to be 4, 2, kan? Then how do you get this and this? Susah nak cuba jaya. So actually there is a formula according to this. The transpose is 4, 1, 7, 2, right? Right? That's the transpose. 4, 7, 1, 2. Okay. So what is A plus A transpose? Here. So you add these two. You got 8, 8, 8, 4. Ada ong lah. Okay. So half of this is 4, 4, 4, 2. Yeah, half of that. Right? So actually without knowing this, I can already put that, right? So this should be 3. 4 plus 3 is 7. This should be negative 3. Because I want it 1, so 4 plus minus 3. And it turned out that this is skew symmetry, right? Because it's 0, 0, 3, negative 3. Okay, that is by cuba jaya and here and there. But directly using this formula, given A, you can directly calculate A plus A transpose, and then you can put half of this, you get 4, 4, 4, 2. And the other way around, you can calculate that. So you put P is half A minus A transpose. 4 minus 4, 7 minus 1, 1 minus 7, 2 minus 2. And also from here you get 0, 3, negative 3, 0. So already you get this and this by using the formula. Okay, so nothing hard about it, just know that formula and plug in plus and minus. But how do you know this works? How do you know that this, how do you even prove this theorem? So we have to prove 3 things. That really, by the formula, S plus P is A, and then that S and that P is really symmetric and skew symmetric. Okay, this is what you have to learn and get used to proving theorems. All right. Don't be scared about the word proof. I was scared masa kita 4 kan, at math, modern math kan. Proof ni macam phobia pula, buktikan. Actually, it's not that, bukan not that hard lah, not that scary pun sebenarnya. Alright, okay. So what we will do now is to prove, yeah? To prove, first, I want to prove that A is S plus P. Very easy. Just add these two. Add these two. So, proof. S plus P is 1/2 A plus A transpose plus 1/2 A minus E A transpose. Darab je lah, kan? 1/2 A plus 1/2 A transpose plus 1/2 A minus 1/2 A transpose. Okay? So, sama ke ni? This one is this one. This is half of A plus half of A equal to A. So it is S plus P is A. Yeah? Tadi pun kita dah. Alright, this is the easy part. Now, I didn't say the hard part, the not so easy part is to show that this is symmetric. Okay? Show S is S transpose. And P, negative P is P transpose. Or P is, doesn't matter. P is negative P transpose of P transpose equals negative P, sama je kan? Okay? Okay? Tak nampak pun jempol-jempolnya. Tertekan raise hand pula. Tanya soalan. Okay. Okay. Now we have to show this, yeah? So just take S transpose. So let me find another color. Okay. So S transpose is this whole thing transpose. Okay. Transpose is actually for matrices. Number you can take out. You don't transpose number. Tiada pula yang transpose tengah jadi 2/1 ke apa kan. Don't transpose the number. So this is just half A plus A transpose transpose. You remember the property of the transpose just now? When you transpose back, right? So this is half. The plus this one, this property. Right? So you just put A transpose plus A transpose again transpose, right? Which is just A. But this is not yet the same as. But we know A plus B is B plus A, right? In the matrix. So you just rewrite as the definition of the S. So which is equal to the original. Tak boleh contoh dinding. So it's half A plus A transpose. Okay. Saya tulis sini, jangan marah. Cuba saya tengok sikit. Kalau pakai laptop ke PC ke, boleh nampak lah. Walaupun comel macam tu. Okay, it's okay. Alright. My view is my gallery view, so I can see the faces. Okay, I want you to try to show this is skew symmetric. I give you 2 minutes. Show this. Using very similar method. Just that you have to find this and then this. Using this. Once you are done, whoever want to share, you raise your hand, yeah? Macam dulu sekolah, saya ingat sekolah. Cikgu kata, okay, siapa dah siap hantar, boleh rehat dulu. Wah, suka. Okay, we have one. Okay, okay, alright. Siapa yang saya tak panggil nama lagi yang dah angkat tangan tu? Nak volunteer? Unmute. Peter Chai, did I call you before?
No yet.
Not yet, okay. Alright, you will help me, yeah? So,
Okay.
you want to show negative P is P transpose, right? So you
Yes.
take transpose first, yeah? Okay. Cakap lah.
Okay. 1/2 A minus A transpose. Transpose again.
Okay.
So number remain the same.
Okay. So
A
that is
transpose minus A,
okay.
and take out the negative.
All right. So this is 1/2 A transpose minus A, yeah?
A, right?
So I want it to be, this is the other way, right?
The black,
Okay, so I
the A
take out what?
transpose and A,
Negative. Yeah, okay. So now it looks like
P,
this.
negative
Okay. So negative
P.
half P. All right.
Negative P, right?
Negative P.
Yeah.
Okay. Kalau cikgu kan dia kata saja je nak tengok buat semak ke tak semak ke. Okay, Peter Chai, thank you.
Okay.
Any question from the others? Okay. We will have a 5-minute break. Okay. And after coming back from break, or you can do this during the break, there is exercise 1. If you have your notes with you, I want S, but I will write the question here, yeah? It's given as exercise 1 on page 9. A is 246 0 2 0 negative 2 negative 2 4. So find S and P, yeah? So that A is S plus P. Before we go for break, saya pun nak cari air ni. Ni ada lagi yang kat tangan ni, kenapa ni? Saya tengok sikit. Ellie, dah ya? Lupa pula nak turun tangan. Penat tau, kat tengah dalam kelas macam ni. Okay, what's the answer?
For last answer or what?
Mana ni yang bercakap ni? Tali tak habis ke?
Oh, me.
Nabil ke tu?
Ya, saya. Unused lecture.
Sebab nampak macam potato ada rambut merah.
Memang begitu. Macam dah muka.
Macam. What's the answer again?
For S, 222.
Huh?
For S, 222.
222.
It's from that. 222, 22 negative 1.
2,
2,
2,
negative 1.
negative 1.
2, negative 1, 4.
Okay.
And for 0 to 4, negative 2, 0, 1. Negative 4, negative 1, 0.
So you can check actually your answer whether this is symmetric. Doesn't matter, right? Symmetric. Skew symmetric 0, negative. Then when you add, you get the original, right? So just use the formula that S is 1/2 A plus A transpose and P is 1/2 A minus A transpose. Tak perlu cuba jaya, then you're just wasting your time. Okay. 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 Right. Boleh padam? Okay. All right. Okay. Next, we have to move on to other types of matrices. Number 7, yeah. Diagonal matrix. Okay, what is a diagonal matrix? A diagonal matrix is a square matrix. Okay. A is an n by n matrix. It's a square matrix in which all of the entries not on the main diagonal are 0. This is the condition. All of the entries not on the main diagonal are zeros. So if Aij, I is not j, which is not on the diagonal, then it has to be 0. All right. Example? Like this. 2, 0, 0, 1, right? This is a diagonal matrix because, or we have like 1, 2, -1, and the rest zeros. Some books, some authors write the matrix as this. These are all zeros, right? D with that one, just the symbol. Okay, this is diagonal matrix. Question, is zero matrix a diagonal matrix? Yes or no? Type in the chat. Is zero matrix a diagonal matrix? I see all yes. Okay, so all answers are yes. Because you don't care really about the diagonal entries. You just want to look at the non-diagonal entries, right? They are all zeros. So yes, zero matrix is a diagonal matrix. Okay. And identity matrix also is a diagonal matrix. All right. Now we have next, number 8 is upper triangular and lower triangular matrix. So upper triangular matrix, so Aij is 0. So you have like A11, A21, AN1, star 0. For all I bigger than j. Because for anything below this, you remember when I write like this? All 1, right? This one. Underneath this, right? I is bigger than j, right? I is bigger than j. It's always I is bigger than j. So for I bigger than j is all 0, is upper triangular matrix. And for lower triangular matrix is the other way around. We have this till A. Okay, we have this, and we want this 0, right? And the rest is, doesn't matter. The star means doesn't matter. It can be 0, it can be numbers. Okay, so for the lower triangular matrix, for I less than j, this one, all I is less than j. That is what it means. Okay. A diagonal matrix is both, right? A diagonal matrix is both, because when it's bigger, when it's smaller, it's 0, right? When I is not j. Okay. The last part, I think, is it the last? Oh, before that. A sub matrix is number 9. Sub matrix. Any matrix resulted from eliminating rows and columns. We call it a sub matrix of the original matrix. Okay. Any matrix resulted from eliminating, deleting rows or columns is called a sub matrix. So if you have a matrix A, eliminating S row or an R column. And our row, we have M row, so S can be, don't eliminate any row, or eliminate M-1 row. You cannot eliminate M row. If you eliminate M row, you eliminate everything. You have only M row, right? And R, N. Okay, you eliminate, it becomes a submatrix. So in the example, we want to find all submatrices for B. 1, 2, 3, 4, 5, 6. Okay, so this is 2 by 3. Okay, this is 2 by 3. You can eliminate one row, right? You cannot eliminate 2 rows, then it's gone. So you can only eliminate 0 row or 1 row. You can eliminate 0 column or 2 column. Okay, let me show by elimination first. So as an example, try to eliminate the first row. Okay, eliminate the first row, we will get 4, 5, 6. Eliminate the second row, we get 1, 2, 3. Right? That is eliminate. Eliminate rows. So eliminate S is 1, R is 0. Right? So eliminate 1 row. I don't eliminate any column. Okay. Now, if you eliminate 1 row, 1 column, 1 row, 1 column, what will you get? Like you eliminate this row and this column, right? Or this row and this column, and this row and this column. So you will get like 1, 2, 1, 3, 2, 3, 4, 5, 4, 6, 5, 6. This is eliminating 1 row, 1 column. Okay, so if I eliminate this 1 row And this one column, I get 1, 2. If I eliminate this, 1, 3. This, 2, 3. Right? This, 4, 5. This, 4, 6. This, 5, 6. Okay. Then I can also eliminate 2, right? 2, 2 column. I can eliminate 2 column. Like this, that. You can get only 1 left, right? So that's why I have that in the notes. I have 1, 2, 3, 4, 5, 6. This is actually by eliminating 1 row and 2 column. 1 row and 2 column. 1 row and 2 column, like this. But whatever is left is the one by one. So to make things easy, when you have a 2 by 3 matrix, so I started by a 2 by 3 matrix will be, I will have like 1 by 1. Yeah, 1 by 1, and then 1 by 2, and then 1 by 3. Okay. But I haven't finished. Okay. If S is 0, R is 0, if S is 0, R is 0, you don't eliminate anything. It is the original matrix. So the original matrix is also a submatrix of the original matrix. Yeah, because S can be 0, R can be 0. So the whole B is also a submatrix. So another one is B, right? But I can eliminate 0S and then change the R, right? Change the R. So I can eliminate, what if S is 0, R is 1? This one, all S is 1. Don't eliminate the row. Just eliminate the column. So I eliminate column 3. I eliminate column. Right? That is eliminate 1 column. What about I eliminate 2 column? Eliminate 2 column. What's left is just the 2 by 1, right? So you just can copy 4, 2, 5, 3, 6. This is the right explanation by eliminating. Okay, when you think about eliminating. The one that I have in the notes is about what's left. So from the 2 by 3, I just write down what's left. It's much easier actually. Rather than thinking of eliminating, you just go direct to what's left. So by 2 by 3, you can get 1 by 1, 1 by 2, 1 by 3. There is no 4, right? So, and then it start with 2 by 1, 2 by 2, 2 by 3 is the whole one. And then what is the 1 by 1? You just take 1, 2, 3, 4, 5, 6. What is 1 by 2? Right? This is 1 by 2. What is 1 by 3? So this is 1 by 3. What's 2 by 1? This one. What's 2 by 2? This one. What's 2 by 3? The whole one. So this is the list of all submatrices of a matrix. I will always think about what's left rather than what to eliminate, right? It's a little bit confusing to, okay, I eliminate this, all right? Okay tak? Okay, is it clear? Okay, okay, okay. Exercise 2. Exercise 2. Ada yang dah buat. Dia nak tahu betul ke tidak. Okay. Siapa yang belum buat, boleh buat sekarang. We'll do it fast. I will. Kalau the book that printed out, it's right easy to write or refer. But if I think everyone is buying the book, then I will give you more examples. Then you can have more, the one that outside the one that I give you, so you get extra. Okay, so the deadline is, when is the deadline for your notes? Tomorrow or today? Bila Hana?
Tak mention, tapi saya rasa elok by this week kot. Sebab nanti
No, I
kita
give a
ada-
deadline.
Okay.
There's a deadline in the, mana telefon saya? Because I want to send to the shop. Ui, banyaknya message. Deadline Wednesday, 23rd March. Wednesday is tomorrow, 11:59 PM. Tak ada masa kan? Okay. Then I will go for the first batch, and then if you are late, then you go in the second batch next week. Okay, question. Okay, this is 3 by 4. The question is, find all submatrices. Find all submatrices for this matrix A. So you can just have 1 by 1, 1 by 2, 1 by 3, 1 by 4. Then you have 2 by 1, 2 by 2, 2 by 3, 2 by 4. Then you have 3 by 1, 3 by 2, 3 by 3, 3 by 4. Because you have 3 rows and 4 columns. Okay, then? Yes, no? Not done? Quick, quick, quick. Okay, so you know that you have to get one by one. So you will do 3, 2, okay, it's a matrix, yeah? 6, 5. You don't need to repeat if it's the same entry. If you repeat, it's also okay. Because it will show that, oh, I missed 1 0. Different deletion, right? For this one. So just type right all. Then for a 1 by 2, you just take any 2, right? I'm not gonna go every single one, but 3, 2, 3, 6, 3, 5, 2, 6, 2, 5, 6, 5, and you can finish all, right? This is the first row, so plus another 12. From the second row and the third row. And this one you have 3 to 6, like 3 to 5, 3 to 6, 3 to 5, 3, 6, 5, 2, 6, 5. So this is by deleting one column at a time, right? If you're not sure how you delete. Plus 1, 2, 3, 4, plus 8 more, right? From this one. This is easy. This is 3 of them. 1, 2, 3. 2 by 1 also, for example, you have 3, 2, 0, 1. You delete 1 row and 2 columns at one time, but there are many combinations. Okay, you don't have to finish it now. Just at least you know what it looks like. Silap. I meant this for this one. 2 by 1 is just 2 by 1 like this, right? Like 3, 0. Don't go like this. 3, 0, 3, 1, right? And then 2, 1, and then 2, negative 1. Right? And then go that way. There is another 4 more, right? No. Some more. You have also 0, 1, right? 3, 0, 3, 1, 0, 1. 2, 1, 2, negative 1, 1, negative 1. Plus 6 more. And 2 by 2, and then 2 by 3, for example. That's 2 by 3. 2 by 4 is easy, right? 2 by 4 is just 1, 2, 3. 3 of them. 3 by 1 is also easy. That's 4 of them. 3 by 2. So you don't remove any 3. You just remove 2 at a time. So you will have 3 by 2, 1, 2, 3, 4, 5, 6. 3 by 3, you just remove one column. So there are 4 columns. Yeah, that's why you know how many. It's by how many that you have to remove. And that's one. So when you go back, you can finish. Okay, I have to move on because we still have. Okay. Number 10, I will just say this, yeah. I don't have to write. A row matrix is 1 by n is row matrix. So for this one, this is a row matrix, yeah. This is a row matrix. 1 by n. This is a row matrix. N by 1 is a column matrix. Column matrix, just one column like this. This is a column matrix. This is a row matrix. All these are row matrix. If a singleton like this, it's a column matrix and also a row matrix because it's just one by one. Okay, this is one important matrix. Next is number 12, nilpotent matrix. Although we have not seen the operation, I assume you know how to add, how to subtract, how to multiply matrices, because this is using multiplication or power. A square matrix A is called nilpotent if A to the K is the zero matrix for some K, positive K. Okay. And K is called the index of definitely a zero matrix is nilpotent of index 1 because zero matrix is O to the 1, right? So a zero matrix is nilpotent of index 1. If you see this matrix, you multiply and see how many times will it be ever go to 0. So you try, if this is A, try to multiply it, right? 0, 0, that's definitely 0, right? So A squared is the zero matrix. So we say A is nilpotent of index 2, right? And over there, I give another matrix 3 by 3. Okay, straightforward. All right, next, number 13 is orthogonal matrix. I'm not sure if you have heard, but I think you have heard about orthogonal. Probably not orthogonal matrix, but I'm sure vectors that you learned during secondary school in modern math mentioned a bit about two vectors being orthogonal in which they cross at 90-degree angle, right? Ingat ke tidak entah. So actually, there are two definitions of orthogonal matrix. First definition is that if A is a matrix by vectors as the columns and let me think. Okay, yeah. There are two things, yeah. Vi dot Vj is 0. Okay, for I not equal to j, and the norm is 1. You have learned this during your math before. This is what we have seen. This is the dot product, if you remember. This is the dot product equal to 0, meaning any pair when you multiply, any two different pair, if you multiply, is equal to 0. And the norm of each one is equal to 1. It's a unit vector, right? You have seen this before. How do you multiply? So if you remember this, suppose V1 is this, I call it Vi, yeah? And Vj. I use something different. Okay. So Vi dot Vj that we have learned from before, the dot product or the norm or apa dulu tak belajar dah tak ingat. Dot product lah. So you just multiply the accordingly, right? This times this plus this times this and this has to be 0. Okay, for A to be an orthogonal matrix. And what is actually this? The norm of this is the square root, right? X1 squared plus X2 squared plus Xn squared. This we have learned before. But in this class, because we're dealing about matrices, orthogonal matrix is such that A inverse is A transpose or A transpose times A is I. Oh, this is equal to A times A transpose also. Okay. Okay, let's see. Things are easy to see with examples. Okay, what's the example? Let me see. A is 2/3, 2/3, 1/3, negative 2/3, 1/3, 2/3, 1/3, negative 2/3, 2/3. Okay, wait. Okay. So this is your first. Hilang dah definition dia. This is your first vector, the second vector, the third vector. All right, so let's try and do this both ways. All right, so you have V1, you can write as the column or you can also write as row, but sometimes when people write column as row, they put a transpose, but it's okay. Anyhow, so I will just copy like this. V1, right? V2. And V3. Okay, so you have to check whether V1 dot V2 is 0, V1 dot V3 is 0, V2 dot V3 is 0. So V1 dot V2 is, you multiply this, negative 4/9 plus 2/9 plus 2/9, which is equal to 0. All right. Then you check V1 dot V3. So again, 2/9, negative 4/9, 2/9. So this is also 0. Yeah. And then V2 dot V3, you multiply this 2. So negative 2/9 plus negative 2/9 is 4/9 plus 4/9. So this is also 0. And then you have to check whether the norm is equal to 1. So the norm of this V1, so you take this will be 2/3 squared plus 2/3 squared plus 1/3 squared, which is equal to 4/9 plus 4/9 plus 1/9, which is 1. And you see that this is 2/3, 2/3, 1/3, 2/3, 2/3, 1/3 with plus or minus 2/3, 2/3, 1/3. So it's exactly the same method, because positive and negative, when you square, you get the same value, right? So all of them, you will get this value, and you have to show also that this is equal to 1, and also V3 is equal to 1. So by the first definition, then you can show already that any Vi dot Vj equals 0 and the norm is 1. We will try and see whether when we transpose and we multiply is equal to the identity. This is actually much easier because you just need to multiply once. Okay, is this okay? Jempol, jempol, jempol. Okay, ni nak padam. Alright. Okay. So I will erase this. And we start with the multiplication. Alright, so A transpose is equal to, so you just copy the row as column. Then you multiply, and then you show it's equal to I. Whether you do it from left or from right. Okay? So A transpose is 2/3, negative 2/3, 1/3, 2/3, 1/3, negative 2/3, 1/3, 2/3, 2/3. Multiply. So A, this multiplying by this is similar to multiplying just now, right? Vi and Vj, because this is exactly. So you do this yourself, 4/9 minus 4/9, and so forth, right? You will supposed to get, you multiply, right? This is what you have to multiply. So 9/9 is, you show that it's equal to this. Then you see that this is an orthogonal matrix if it satisfies all. If only one or at least one is not satisfied, then it's not orthogonal. Right? You don't have to show all not satisfied, at least one. Okay, the easiest one, you can just multiply or you just find the norm. Yeah. This one, so you see that to show it is not, it's much easier maybe to use vectors. Yeah, because you don't have to write out all this. Okay. So many type of matrices. Oh. That's another one which is called Hermitian matrix. You should Google. There is a mathematician named Hermite. Whether it has something to do with this matrix or not. This is a square matrix with complex entries. All of you have taken complex do you remember complex numbers in high school? Yes, no? Yeah? You remember this number? With the imaginary? Type lah sikit, yes ke, no ke? Okay, a square matrix with complex entries. Okay, this is called Hermitian if A transpose bar is A, or A bar transpose is A. So it's either you transpose first, then you take the bar, conjugate. You remember conjugate? If Z is equal to this, Z conjugate is A minus BI. Yeah, so this is the conjugate. So this means AJI bar is AI. You transpose and then you take conjugate. So as an example, 2, 3 plus I, 3 minus I, 5. Okay, this is summation. And you can determine what the diagonal has to be and the mirror image has to be. Similar like we did before with the skew symmetric matrix, right? Oh, still have 2 more. That's okay. Let's finish this. So for IJ, okay, AII bar is AII. If AII is X plus IY, AII bar is X minus IY. Yeah. If AII is AII bar, this means X plus IY equal X minus IY. Okay. X is equal to X is okay. This means Y is negative Y because we equate the imaginary part. And this gives 2y is 0, which gives y is 0. And what does it mean by y is 0? Y is 0 means AII is just a real number. It's just R without the I. When y is 0, AII is just a real number. And you see this diagonal? There is no I, no imaginary number. It has to be just real. Okay, this is the condition. So when I is j, AII must be real number. And when I is not j, the transpose is the conjugate of the other one. Right? The mirror image is the conjugate. So if this is 3 plus I, this is 3 minus I. This is to see whether or to find examples. To show, you have to go through this. You have to take the transpose, and then you take the bar, meaning the conjugate, and you see it's equal to it. I'm not going to go through the detailed example because I have just a bit more before we stop, yeah? It's already 1 o'clock. But we have 2 more that I will just write out the definition. Number 15 is the unitary matrix. Because this you probably have not heard before. Unitary matrix is also a square matrix with complex entries. A bar transpose A is A transpose bar is pi. Very similar to just now, right? Orthogonal matrix. But if it's complex, it becomes unitary. Yeah. Hermitian is a little bit like the symmetric, but with the complex. Unitary is a bit like orthogonal with complex. And last one is skew Hermitian. It's like skew symmetric. It's skew Hermitian matrix if A bar transpose is negative A. A bar transpose or A transpose bar, they are the same. Okay, so you have symmetric, skew symmetric, then you have Hermitian, skew Hermitian. Okay. Okay, so although actually I had to finish this week with operation, but I have started that with the quiz. That is the operation. So go through the notes under matrix operation, addition of matrix, properties of matrix addition. These are all very familiar to you. And then we have multiplication by scalar. Subtraction is just doing addition and multiplying by -1, right? And there's empty spaces that you have to calculate. And how do we multiply two matrices? All right. I will go a bit about this in our next class next week. We have next week, right? Sunday. And mention a little bit about trace. Then we will go into elementary row operation. So I will say this. You have to understand elementary row operation, right? Understand fully, because whether you pass or fail the class is based on elementary row operation, because you'll be using this until the very last chapter. So it's very, very important. That is my point. Elementary row operation is the key to the whole of the linear algebra class, because you will be using it until the end of the semester or chapter 5. Okay, I'm really sorry that I probably passed a few minutes. Any question?